And so our air actually has a path that's the sum of those two directions. And instead of looking at mass times acceleration, what I want to look at is this little component, this velocity. So once you've got the curvature and once you've got your wing, you don't really have any control over how fast this is going to go down. You can only pull the air so fast with this curvature and a particular horizontal speed. So we're going to assume that that speed is staying the same. But what we're going to do is try to pull down as much mass, as much air down towards us as possible. The more quickly we can pull the air down, the more force that the air is going to put on the wing, creating more and more lift. So we're trying to pull mass at a particular rate as fast as possible. Pull molecules out of the air downwards. So we're going to call that the change in mass per time, dmdt. Instantaneous rate of mass change times the velocity that we're going downwards, the air velocity. And so in this equation, what we're doing is we're taking this mass, this little part of the equation, and we're asking ourselves, what is dm dt? What does it depend on? And you can't see the equation, so I'm going to try to write them here. First, you're going to have the density of the air that you're pulling on. And really what you're trying to do is, given a certain density of air, you want to pull as much volume of that air as you can. So in order to get a lot of mass being pulled down per unit time, given a constant density, the part that you have control over is how much of that air at constant density can you pull. How much volume can you grab and pull it down? And the volume is basically going to be a component of area, right, times a direction, a length direction. So you have an area times a length direction, right? So this is still volume per time. But now I've got a set area of the wing, the density of the air, and this is how fast the air is moving across the top of the wing. Not the downward, but the horizontal. So this turns into, I call it lambda, so you don't get it mixed up with this letter right here, the downward velocity. And then the area of the wing, it's a different way to measure it, but the way we measure the area of a wing is not so much length times width, but it's more just how long it is. The area that's effective for flight is not the width of the wing, but how long the wing is. So area, we're going to measure it as half the wingspan, how long the wing is, squared, times lambda. So this is how quickly we can bring mass down. Density, the length of the wing, times how fast we travel through the air. Which means my equation can now be, whoops. So here's an equation, and it says the force, which is really the weight of the airplane. The weight of the airplane is equal to how quickly the air is moving downwards, which is a property of how much curvature you have on the wing. What the density of the air is, how long the wings are, and how quickly you're moving through the air. What's your velocity, your horizontal velocity. So if you want to pick up a lot of weight, you could go really fast. You could make the wings really long. You could go through very high density air, which is low altitude. Or you could somehow make the curvature enough to bring down enough velocity in the vertical direction, throwing down air vertically. So there's an equation that basically tells you, if you knew what weight you had, you could calculate what you would need to either how fast you go, or the wingspan, or the density of the air, or any of these things. There are relationships that you can sort of predict what weight you can carry. Or if you had a certain amount of weight that you had to carry, you could solve that equation to figure out how fast would you have to go to be able to carry this much weight. And like I said, you can just, if you want to see it work, you can expensive. Okay, I thought this was very interesting, the power that you need to one is the fact that this is an object traveling through the air. You've got drag. You have forces that are pushing on the airplane, and they're called drag forces, and you have to overcome them with power. So the power, the total power that you need is, I'll write it up here, it says W squared over dB squared, and then there's, I'll write it down, 1 over lambda. And then the other one is coefficient of drag, density. Okay, so the power that you need to generate in order to fly is partly due to the power that you need to take off, and partly due to the power that you need to overcome the drag of this aircraft. So here's the variables. You've got the weight, you've got density, you've got the length of the wing, the wingspan, and lambda, once again, that's your horizontal speed. And here is the cross-sectional area of your aircraft. So if you look at the front of a plane, the air only sees this big, it only sees how much area is relatively flat to the front. In other words, direction, cross-sectional area. This right here, this is the coefficient of drag. It's how much drag, not the number that equates this shape. How much drag would this be? How big would a circle have to be in order to be the same amount? And once again, here's density and here's my speed. But when you have the plane, once you've built it, this thing right here, you can't change it. Once you've built it, it already weighs something. Things are already law. Density, you can't change that. It's all drag. You can't change these things either. You've already built the plane. So the only thing you can do to generate power is to go faster. Right? So here's what this equation says. For low speeds, this is the reciprocal of a number. So if you want to have a lot of power for takeoff, you have to, let's see, the bigger the speed gets, the smaller the fraction gets. So the bigger takeoff speed you have, the less power you need to take off. On the other hand, the faster you go, the bigger this term gets. So the faster you go, the more drag there is on this vehicle. So together, I don't know if you're studying Math 111 or not, but this is a perfect example of the combination of functions. If you take a look at a power function, which is 1 over lambda, if you study power functions yet, the power function typically for positive speeds, not negative speeds, for positive speeds, this term behaves like a power function. And for positive speed, this one behaves like a cubic power function, which essentially looks like this. And the sum of these two functions, when you add them together, when you take this little height and add this little height, you get this little height. And the sum of those two functions is another function, another formula. And so that's what we're looking at here. If you add the two equations together, the result is this red formula, the combination of two other formulas. And it's the total power you need to fly an airplane. You can predict how much power you need based on how fast you need to go. I thought that was good. Okay, safety. There's nothing like destroying a carefully engineered airplane with a bird. I thought this was an interesting aspect of safety. I don't know if you remember the article. I think it was in New York or New Jersey. It was a big deal. There's this pilot flying out of LaGuardia Airport. And about 2 minutes after taking off, a flock of birds flew through his engines. And they knocked both engines out. They didn't work anymore. And he crash landed on the Hudson River. It was all over the news. But that was a classic problem due to bird strike. And it's been a problem for years. I mean, when I was looking through the web, I saw pictures of falcons stuck to the nose cone or the windshield of airplanes. But it's when they go through your engines that makes a big deal. So bird strike, high